If you record a hologram of a simple point in space, the exposure pattern on the film is this Fresnel zone plate. Concentric rings that get spaced closer together the farther you go away. In fact, you can be a little bit more quantitative and write down the exact spacing between those fringes. Let's say you draw a line from a point on this film down to the object, or maybe I should say down to where the object was during recording. Consider the angle between this line and the one perpendicular to the film, which I'm going to call theta prime to distinguish it from the diffraction angles we were just looking at. I won't narrate through all the details here, but you can work out this fringe spacing exactly. You start with the premise that the distance between adjacent fringes to the object should differ by one whole wavelength. I know some of you are curious and want to pause and ponder, so I'll leave up the details, but the upshot is that it all boils down to a delightfully clean and convenient fact. The spacing between the fringes for our Fresnel zone plate, which I'll label as D, multiplied by the sine of this angle, theta prime, equals the wavelength of the light. This might give you a little déjà vu, and if it strikes you as uncannily similar to the diffraction equation, you are 100% right, and it's the key to how our first hologram works. When you just shine the reference wave through this pattern, near a given point on the film, it acts like a diffraction grating, splitting the wave into distinct beams, and the angle of those first-order beams satisfies the diffraction equation, d times sine of theta equals lambda. Therefore, the angle of one of these first-order beams exactly matches the angle of the line connecting this point of the film to where the object was during recording, even though the object isn't there anymore. So, critically, think about why this would imply there's the illusion of a point behind the screen. For an observer on the other side of that film, as the reference wave is shining onto it, every point of that film is emitting multiple different beams, but one of those beams at each point matches what a beam from that object dot would look like if that object dot were still there. So the observer always sees this bright spot on the glass at a point where a line from their eye to the past object position intersects the glass. As they move their head around and their eye moves in 3D space, that apparent bright spot on the glass moves with them in just such a way that it gives the illusion of a floating point of light behind that glass. The way things are set up right now, the other beams would add some distraction for that observer. The 0th order beam, for example, at all of these points, is essentially a rescaled version of what the reference wave would look like if the film weren't there. To the observer, this looks like a bright glow coming from everywhere behind the film. This would be pretty obnoxious, but it can be solved by shining the reference beam in at an angle. Now you might be curious about that other first order beam, and it's actually very interesting. If you draw a line along that other first order beam from every point at the film, all of those lines converge at a single point on the opposite side of the film. This is our first peek at a funny little artifact of holography known as the conjugate image. Much earlier, I said that the way you want to think about a hologram is that you're trying to record and reconstruct the state of the light field around a scene. The truth is that a hologram doesn't exactly do this. What it actually recreates can be thought of as a sum of 3 different light waves. One of them is a scaled copy of the reference wave, which for our simple point example corresponds to the 0th order beam. Another corresponds to a copy of the wave emanating from the object. This is exactly the thing we want to reconstruct, and in our simple example, it corresponds to one of these first order beams. But there's also a third wave in there. In this simple example of a hologram of a single point, that third component looks like the reference beam being concentrated in to a single reflection of that point through the film. More generally, though, this third component looks like the reference beam being refocused onto a reflected version of your full object on the opposite side of the film. In the hologram that we recorded with Craig and Sally, you can actually see this by putting a piece of paper behind the glass, where at the appropriate distance away, you see the light focused onto the shape of, for example, the pie creature, which was part of the scene we recorded. This is known as the conjugate image. In the earliest days of holography, Denis Gabor had a lot of trouble seeing the holograms that he wanted to because this conjugate image kept getting in the way, muddying up the waters. However, again, this is something where if you use a reference beam that shines on the film at an angle, you can get a clean separation of the reconstructed object wave from this conjugate wave artifact. The astute among you might ask about the higher order beams from a diffraction grating. After all, we saw how the equation doesn't just imply 3 beams. For large enough values of d, you can have many more angles that satisfy the diffraction equation. This is something I actually didn't know until learning about holography, but if instead of a binary grating, where light either completely passes through or gets completely blocked, you instead have a material that only partially allows light through with an opacity that follows a sine wave pattern, then you actually don't get higher order beams. The diffraction pattern only includes 0th and 1st order beams. The most elegant way to show why, in my opinion, comes from the more formal explanation of holograms that I want to show you in a few minutes. But for right now, just know that it means you're safe to only think about 3 beams emanating from each point of the film. So, stepping back, you, the problem solver puzzling over holography, have at least this one example to hold on to. A hologram of a single point gives a zone plate, and the diffraction effect of shining the reference through the zone plate includes, among other things, a recreation of the wave from that point. A natural place your mind might go from here is to wonder about 2 such points in space. Right here is a simulation for what the resulting exposure pattern would look like. It's based on adding the 2 radial waves from those points together with a reference wave, and you can clearly tell that it's related to the zone plate associated with each one, effectively encoding 2 distinct 3D positions. But it is more complicated than simply adding the 2 individual patterns, in the same way that the double slit interference is more complicated than simply adding the brightness from each individual slit. The result depends on how the waves and their phases interfere. Even still, you can see how this might lead you to think about building up a scene as a combination of multiple points, and hypothesizing that the resulting exposure pattern can be thought of as some kind of combination of the zone plates for each one. The simulation I'm showing you has only 30 points, and already the result effectively looks like random noise. But nevertheless, I think you would agree that a reasonable hypothesis would be that the diffraction effect of shining a reference beam through this pattern might be the sum of what you would get from the zone plates associated with each individual point. And you know that looking through from the other side of this film, it would give the illusion of those 30 points being there. If that were true, you could think of a more complicated object or more complicated scene as a continuous cloud of many little points, and the resulting pattern would not only encode the 3D position and orientation of that object, but it would also enable the simple reconstruction that we're looking for. As stated so far, this is all sketchy and non-rigorous, but it does actually lead you to some very real intuition about how holography works in practice. Think back to the very start when I asked you to appreciate how much information is being stored on this film, in that it can recreate a scene from a wide continuum of viewing angles. Part of the catch is that for this process to work, the film has to have extremely high resolution. For comparison, standard Polaroid instant film resolves only around 10 lines per millimeter. Microfilm will get you somewhere a little over 100 lines per millimeter, but the film that we used to record this hologram can resolve many thousands of lines per millimeter. And now you know why this is necessary. The spacing between fringes in a zone plate becomes very, very narrow, and faithfully recording those variations is necessary to reconstruct the object beam at that point. Without the outer fringes, the effect for a viewer would be that they simply don't see the object if they're viewing from a sharp angle. This is not a complete explanation without justifying how exactly the exposure pattern that you get from multiple points would have a diffraction effect that equals the sum of what you would get for the individual points. Even then, there's a deeper issue. Building up a scene from individual points would not do true justice to the power of holography. The reason we included that glass Klein bottle in our example is to emphasize this power. That glass does not act as a collection of points, merely reflecting light. It affects the surrounding optics of the scene, like how the light from the objects behind gets bent and distorted as it passes through. The hologram perfectly recreates this effect in a way that could not be explained by adding up individual points. Anyone who has experience with ray tracing will appreciate the difference here. Also, the sharp-eyed viewers among you might have noticed a couple gaps in the explanation even for a single point. For example, I mentioned shining in the reference beam at an angle, but that would also change the exposure pattern. so it's not entirely clear that the logic still works. Sometimes in math, a complex problem can be solved incrementally by building up simple cases, but other times, the simple cases act more like training exercises, and the best way to tackle a general situation is to set up a new framework for thinking about it, such that the general solution simply falls right out. In the case of studying holography, there is an entirely different and more powerful way to explain holograms that subsumes all of these issues. I'll walk through it at the very end here as a kind of technical appendix to the whole video, but I think it would be nice to wrap up the main discussion by stepping back and discussing holograms more broadly. Everything we just described covers a transmission hologram, the simplest variety, and these have been possible ever since the late 60s. More advanced techniques exist where the film can reproduce the scene not using a laser, but with ordinary white light reflecting off of it. And it goes beyond that. There are techniques where you can make changes in the scene over time visible as you view the hologram from different angles, or where you can take a 3D computer graphics model and produce a hologram of it. You and I covered the bicycle, but people went on to invent cars and planes thereafter. In our example, we were modeling the film as a two-dimensional surface with no thickness, and that's perfectly okay for transmission holograms, but it's worth noting that that changes for white light reflection holograms. Variations in the exposure through the thickness of that film become relevant for filtering out the appropriate wavelengths during reconstruction. The fact that Denis Gabor won a Nobel Prize should give you some hint that the significance here goes beyond its use as an art form. That clip that I showed earlier where we delicately touch the object with a feather is displaying the original scene superimposed with its own hologram that we had just freshly recorded. The dark stripes that you see on the pie creature arise from the extremely tiny shifts in position and how that affects the interference of the light. And you could actually use that to measure the size of those shifts. This gives a very small glimpse into the relevance that holograms have to interferometry, which is the technique of using wave interference to measure extremely tiny distances. More broadly, being able to record and reproduce an entire wavefront is just a useful tool to have in your belt for a variety of experiments. For any of you who want a deeper look at the history and development of holography in physics, I highly recommend reading Gabor's Nobel Prize lecture. Throughout the lesson, I've repeatedly referenced the goal of making holograms feel like something you could have invented yourself. But there's an irony here, because in his own reflections, Gabor describes this not as a deliberate discovery. He called it, quote, an exercise in serendipity, the art of looking for something and finding something else. But luck favors a prepared mind, and the more that you engage with imagined rediscovery of the inventions that you find around you, the better positioned you'll be to, one day, just maybe, have your own moment of similar serendipity. And finally, for the stalwart viewers hungry for the final details, here's the more formal description of why holography works. For the small price of introducing complex numbers into the discussion, the result kind of just pops out from a few lines of algebra. So think about recording a hologram where you have both a reference wave and an object wave shining on the film. We're going to write down the sum of those two waves as R plus O. The exposure pattern depends on the amplitude of this combined wave at each point on the film. And like I said earlier, more precisely, it's proportional to the square of that amplitude. Each of these symbols, say the object wave O, is meant to represent a function that takes in a point in space, as well as a time, and returns some real number value describing the strength of the wave at that point. It's an incredibly complicated function, but at a fixed point in space, this output value simply oscillates up and down over time, which we've been visualizing throughout as oscillations between blue and red. Very often, the math that you do with waves has a habit of becoming a lot more elegant when you treat an oscillating value like this not merely as a real number, but as the real component of a rotating complex number. This might feel very strange if it's something you haven't seen before, but one way to motivate why you might do this is that a complex number very elegantly encodes both the phase and the amplitude of the wave at a snapshot in space and time. The wave amplitude is visible as the size of this value, its distance from the origin, and the phase is visible as the angle this number makes off the horizontal. The physical significance when you model things like this is just that the real component of that rotating complex value tells you the strength of the wave at that point. But you might think of adding on an imaginary component like this as sort of extra bookkeeping that lets you more readily keep track of the phase and amplitude of the wave at that point. For example, the amplitude of that combined wave, the thing we care about to describe the exposure, can now be written as the magnitude of this sum, r plus o, where now we're thinking of that as a sum between two complex values at every point on the plane of the film. So, for example, at places where those two values align, that corresponds to constructive interference between the waves, and the film is going to be more opaque. Where they are out of phase, you get a really small result, and that corresponds to the film being more transparent. Now think about reconstruction, when you just shine the reference wave through this exposure pattern. Let's write the wave immediately on the other side of the film as r times 1 minus the opacity at that point on the film. So for example, where the film is very transparent, r passes through unchanged, but where it's more opaque, r is going to get scaled down. We can go ahead and substitute in the expression for opacity that we have, and then distribute a little. And what I want to do is focus on analyzing this component right here, which is going to be part of the wave on this other side of the film. When you expand this expression and interpret its terms, the truth of holography stares right back at you. To do so, what you need to know about complex numbers is one definition and one fact. The definition is that the complex conjugate of a number, which you typically denote with a star, is its reflection over the horizontal axis. And the fact that you need is that when you multiply a number by its own complex conjugate, the result is the square of the magnitude of that number. So, in our expression, that exposure term could also be written as r plus o multiplied by its own complex conjugate, r star plus o star. The reason to do this is now you have something you can expand algebraically. Although, admittedly, when you do this, it might first look like a big pile of symbols that is very far removed from physical intuition about reconstructing a three-dimensional scene. But give it just a moment here. When you organize the terms the right way, the answer sort of pops out. Whenever you see a value multiplied by its own complex conjugate, just think of it as some real number, some scaling factor. For example, one part in the final expression looks like some certain real number all times r, the reference wave. And what this corresponds to is a scaled copy of that reference wave here on the other side of the film. In our simple point example, that would correspond to the 0th order beam from the diffraction grating off the zone plate. The key term is this part right here. It looks like some real number, some scaling factor, multiplied by the object wave itself. So here you are on the other side of the film during reconstruction, and the expression for the state of the light field includes this scaled copy of the object wave. It doesn't matter how complicated O is. The scene that it comes from could have whatever complicated optics that you want. But here, on the other side of the film, there will always be this scaled copy of O. In our simple point example, this corresponds to one of those first-order beams. And finally, you have this funny little term at the end that involves the complex conjugate of the object wave. This corresponds, as you can probably guess, to the conjugate image, and maybe now the name makes a little bit more sense. This is a difficult term to make sense of, and I'm not going to say too much more about it, other than to show that for the hologram we made, if you flip the film around, you can see this conjugate image as a very bizarre, warped, and reflected version of the original scene. So that is it. A little piece of complex algebra shows why you have a copy of the object wave on the other side of the film. And importantly, there were no assumptions about how simple that object wave is. Also, it makes no assumptions about how simple the reference wave is. You just need to be able to reproduce the same wave that you used during recording, or at least something close to it. Even though this is more powerful, on its own, I would find this explanation very unsatisfying. The breakdown of a single point with the zone plate pattern and diffraction gratings, for all of its shortcomings, gives a lot more intuition, in my opinion. For instance, the algebra tells you nothing about how the film resolution could matter, but the abstract path and all the power that it brings does offer some reassurance that the shortcomings in that first explanation are all surmountable. In his Nobel Prize lecture, Gabor wrote, "In holography, nature is on the inventor's side." You do actually need to say a little bit more to finish the abstract derivation. Strictly speaking, we've only shown that you have a copy of this object wave on the plane immediately after the film. But what you want to show is that it exists in all of 3D space beyond that film. Rigorously justifying this would go beyond the scope of an already long lesson, But it's not too hard a fact to believe. What we're basically saying is that if you have some function that you know satisfies whatever equations light must obey, namely the object wave O, and you have another function describing a steady state wave where you know that O shows up as a component along a 2D boundary like this, then in the free space beyond that boundary, the wave must also include as a component O in its entirety. This actually has a nice connection to the key mystery from the very beginning of the lesson of how a three-dimensional scene could possibly be stored on 2D film. Part of what's required for this to be possible is that light obeys laws regular enough that the state of a light wave in 3D space is sufficiently constrained by its value on a 2D boundary.